Welcome everyone to my talk or our webinar on fuzzing the Linux kernel. My name is Andrei. And so I've been working with the Linux kernel, fuzzing and other stuff for about 5 years now. I've worked a little bit on making bug finding tools like fuzzers and memory detectors. And currently I'm mostly working on memory tagging, which is an exploit mitigation technique. And my experience with kernel fuzzing in particular, I like to split it into three parts. The first one was about fuzzing the network subsystem via syscalls. We found a few hundred bugs, and I even wrote 3 local privilege escalation exploits for 3 of them. Then I worked for a while on external network fuzzing, and this is about, let's say you have a Linux machine and it's receiving external data over the network. And the kernel is supposed to parse network packets. For example, if you have a TCP packet that the kernel receives, it's supposed to figure out which port this packet is directed to, and then based on that, decide which application is supposed to receive this packet. And this is also a source of memory corruption. So if you send a malformed external packets, you can find something in the kernel. And finally, I've worked on fuzzing USB. This is also similar. You connect malicious USB devices to a kernel, and the driver for a particular USB device is supposed to be handling packets or messages from that device. And if there is a memory corruption, that's also a source of errors. So for all of this work, I use syzkaller. So I'm a little bit biased. But in this talk, I don't want to focus on syzkaller too much. I want to give an overview of the Linux kernel fuzzing approaches in general and some of my tips and some references. I'm going to give a lot of references to different things that people did when they approached Linux kernel fuzzing. So for today, we're going to start first with the fuzzing theory in general. So what is fuzzing, how does it work, what is coverage guided fuzzing, and so on. And then we'll try to apply that theory to the Linux kernel. After that, I'm going to describe 2 of the biggest fuzzers, the most famous fuzzers that happened over the last few years. And this is Trinity and syzkaller. And then I'm going to describe a particular approaches that you can use for fuzzing. And at the end, if we have time, I'm going to go deeper into coverage collection for the Linux kernel with KCOV. All right, now let's get started with the first part. So what is fuzzing? Fuzzing is a technique to automatically find bugs in computer programs. And it's really easy to use. You just generate random inputs, you feed it into the program, you execute the program, and you check. If it crashed, it's great, you got a bug. And if it didn't crash, you just keep on going and generating new inputs. So it's really straightforward. You can, as long as you can execute a program, you can use fuzzing and try to find bugs with it. And what kind of programs can a fuzzer target? Well, anything. The simplest examples are user space applications and libraries, and those are quite straightforward. But a fuzzer can also target kernels, right? A fuzzer can also target firmware. Basically, anything that accepts some kind of input, you can target with fuzzing. So the definition that I gave earlier, fuzzing is feeding in random inputs until the program crashes. If you kind of split up this definition into 5 parts, whenever you're trying to make a fuzzer, you have to address each of those parts. The first one is about the program. How do we execute the program? It's straightforward for user space application because you just run it, but maybe it's more difficult for the kernel. And then if you're fuzzing parts of the firmware, it also can be quite difficult to execute them. Then how do we inject inputs? Again, if our program expects inputs on the standard std in, it's easy, but then when you're trying to inject random USB devices and trying to fuzz the kernel, this can be more difficult. Then how do we generate inputs? We can just generate random data, or maybe we can do something smarter. How do we detect crashes? If the application just crashes, if let's say user space application crashes with a segmentation fault, that's easy to detect, right? But then, for example, if you have an out of balance write of just a few bytes, this does not necessarily lead to crash immediately, or maybe it will not lead to crash at all in your particular case. So in this case, we want to be able to somehow detect bugs better than just relying on the application crashing. And finally, ideally, we want to automate the process, and so we don't have to run the inputs manually, run the program manually. So Most of these questions, answer to most of these questions will depend on what kind of target you have, what kind of program you're fuzzing. But there's one that has some common theory behind it, and I want to start with that. And this is one about generating inputs. So let's look at an example. Let's say you have an XML file parser. How do we generate inputs for it if we're going to fuzz it? The most simple idea that comes to mind is to just generate random data. Unfortunately, generating random data doesn't always work. For example, let's say our XML parser expects the input to start with an opening XML tag. In this case, if we're going to be generating every byte of the input randomly, there is a very low chance that we will be able to guess all of the 4 bytes have this particular values, right? So the fuzzer will need a lot of guesses before it can get past the header check. And then inside our parser, there may be multiple headers like that, multiple places where we need to guess the particular values of bytes or stuff like that. So random inputs are not good. I mean, they're good sometimes, but not always. So random inputs doesn't work good. What do we do? Well, the obvious thing is to generate better inputs. Now, how do we do that? And there's been a lot of fuzzing work in the last years, and people have been mainly using 3 approaches to generating better inputs. The first one is about generating structured inputs. That's also called structure-aware fuzzing. The second one is about guided generation. That's most notably coverage-guided fuzzing. And finally, we can just collect a corpus of samples. So let's look a bit closely at each of them. So first of all, for structured inputs, in case we have an XML parser, what we want to do instead of just generating random data, let's try generating correct or more or less correct XML files. So in this case, what we do, we come up with a grammar that describes an XML file. So instead of just generating random bytes, we'd be generating random tags. And those tags can have random attributes. And thinking about the case that we had previously where the XML parser would expect the file to start with an opening XML tag, we can actually build this into our grammar. I mean, in this case, this is the grammar that I took from one of the fuzzing tutorials, and it doesn't have this feature, but can be easily extended. The second thing is about guided generation. So I'm going to explain it on an example. How does it work? So first of all, we choose a random input. Typically, when we use guided generation, we are going to be maintaining a corpus of relevant inputs, and I'm going to explain what relevant means a little bit later. So we choose a random input. We can choose one of the inputs from our corpus, or we can just generate a new one completely. We mutate it. Mutating means changing it in some way. For example, we can flip bits, we can add data, we can remove chunks and stuff like that. We execute it and we see, did we get any new code coverage? So the idea here is that whenever our program tries to execute our input or like to process our input, it's going to execute different instructions depending on the input, right? And based on that, we can understand if our new input any good. If it didn't produce any new code coverage within our program, that's probably our input is not very good and we just throw it away. But if it produced new coverage compared to the input that we already previously processed, that means it is somehow more relevant and we add it back to the corpus. So this way, doing this process over and over, we're kind of going deeper into the code, exploring new instructions, exploring new paths within our program. So this way, we can go deeper and deeper step by step. All right. Previously, this was about coverage guided generation, right? But the guided generation does not have to be only relying on coverage. There are many different types of signal that we can use. Code coverage is the easiest one and more relevant usually. That's why people use it. But you can also, for example, rely on memory state. So let's say each new input that we process, we're going to be tracking a value of some global variable. And whenever this global variable changes into some new value with our new input, we remember that input. So you can still use that in certain cases. This highly depends on the fuzzer, on the target that we're fuzzing. And yeah, but still, I wanted to point out that coverage is not the only signal that we can use. And finally, of course, we can combine guided generation with the structured inputs approach, and we can mutate inputs accordingly. So in case of XML, we can, instead of mutating bytes, or like flipping bits, we are going to be inserting and removing tags. And the final thing that people do is collecting corpus. So in case of XML, you just scrape the web and you collect a bunch of different XML files. And then you start mutating them. You can also flip bits or bytes and feed them into the program. Or you can combine with the previous two approaches. So you can do, first of all, structured fuzzing, although in this case, remember that if your input, so typically when you're doing structured fuzzing, you first are going to be generating inputs in some internal representation, right? And then kind of like converting them into actual XML files. But in case you have an XML file in as your sample, you need to first parse it and convert into that internal representation before you can mutate it. But generally this works just as well. And of course you can combine this with coverage guided fuzzing. And to understand fuzzing better, I think the best exercise that you can do is you can write a simple fuzzer from scratch. And here I linked to articles by people. Basically, they just wrote 100 lines of Python code and they wrote a simple fuzzer for a target that they chose. Some of those fuzzer are coverage guided. You can do all kinds of stuff. I mean, just try to figure out how it works by yourself. And this is a great way to learn about fuzzing. All right, this was like some generic theory about fuzzing. I don't know if you have any questions on that. All right, let's try to apply all that theory to the Linux kernel. So as I mentioned before, whenever you're trying to make a fuzzer, you got to answer these 5 questions. And in case of the kernel, instead of running some abstract program, we're going to be running the kernel. And what I'm going to do is I'm going to describe my thoughts on each of these questions. So let's start with these 2. And these ones are about injecting and generating inputs. So when it comes to the kernel, and actually when it comes to any kind of target, like the very important thing that you need to understand is what kind of inputs does my target have? So what kind of inputs does the kernel have? Kernel is obviously a program and it processes something, right? So the first kind of input that the kernel have is syscalls. So whenever you have a user space application running, it executes syscalls and the kernel is supposed to be servicing those syscalls. So if you're fuzzing the kernel, we can target syscalls. But then if you think more about it, we also have some external inputs. So something that I already mentioned is if the kernel receives a network packet, it's supposed to parse it. If you have a new USB device connected, it's going to send some data to the kernel. And we have like a lot of different other external buses. And in some certain cases, firmware can also interact with the kernel and send some external inputs to it. And this is also a target for our fuzzing. So how do we inject inputs? In case of syscalls, this is really straightforward. You just execute a binary that performs the syscalls, that's it. But in case of external inputs, that's maybe not trivial. So, I mean, if the inputs are generated by hardware, you could take a piece of hardware and actually use it to generate inputs, but that scales poorly and doesn't always work. The other 2 approaches that you can use is actually either injecting inputs from user space or using hypervisor or emulator. So an example, if we're doing network fuzzing, we can actually, there is a thing that's called tuned-up interface. And basically, if you set up the def-tune device properly, whenever you're writing data into it, it's going to be going through the same parsing path in the kernel as if the packet was received externally. There is something similar for USB that's called the gadget subsystem. Together with the dummy driver, you can turn it into something similar. But most of these approaches require some kernel support. So the kernel is supposed to provide a way for the user space to insert, like to inject this external inputs. And another approach that you can use is actually injecting those inputs from hypervisor. An example would be for USB. You can use QEMU and you can use USB redir, which is a protocol for actually transferring USB data from the host to the guest. And this way you can fuzz the kernel. There is a fuzzer that's called vUSBF that does exactly that. All right, now let's talk about generating inputs. As I mentioned, the simplest approach to generating inputs is just generating random data. A little bit smarter approach would be generating structured data. But we have a problem. The kernel does not accept data as inputs. It expects syscalls, right? you could limit your fuzzing service to a single argument of a single syscall, but that would be like, we would like to find an approach that works in general for all kinds of inputs that the kernel has. Okay, so most syscalls are used as an API. So this is something, an API is a term that I personally use. I don't know what the official name for this in the fuzzing community, but the idea is that whenever you use a sequence of syscalls, it's going to be a sequence of calls. Each of the calls can have multiple arguments, and those arguments are structured, which means an argument can be an integer, or it can be a structure, or a pointer to a structure, or something like that. And then some of those calls might return values, and some of those return values might be used in subsequent calls. So here's a small example. This is we're opening some device file with an open syscall. It returns a file descriptor. Then we're passing that file descriptor into a octal as the first argument, and passing a structure as a second argument. And then we close it. And in case of fuzzing the kernel, this sequence of calls is our input. So you can think of it, you could think of like a single input being a single syscall, but that would be wrong because you have these return values that can be passed between syscalls. So typically when you think about fuzzing the kernel by syscalls, you would think of a single input as a sequence of syscalls. And this is what I call API-aware fuzzing. And yeah, inputs are API call sequences. And whenever you're fuzzing, right, you should be generating your inputs according to some structure. In this case, our structure is a call sequence. So whenever you're generating an input, you should be generating a call sequence, and you should be mutating accordingly for coverage-guided fuzzing or stuff like that. So for example, inserting new calls, removing calls, changing arguments of existing calls. And I'd say this is like the biggest thing about Linux kernel fuzzing, and this is what syzkaller realized, and this is one of the reasons that syzkaller was successful. But then we can look at some of the, let's take a break here. Is there any questions about this part? Because I'm going to be talking about more difficult stuff on the next slide.
I don't see any questions in the Q&A or the chat, Andre.
Okay, perfect. Then let's keep going. So this is the input structure for the simplest syscalls, but then we have other syscalls that might work differently. For example, they may not be as straightforward, or they don't accept just simple structures as arguments. So the first example that I have here are the two syscalls clone and sygaction. There might be others, and the idea here, let's look at sygaction syscalls. Let's say you have an API sequence of calls, a sequence of syscalls, and one of those is sygaction. Sygaction can be used to set up a signal handler for one of the signals. And essentially, whenever that signal would be triggered, the kernel would transfer the execution to your to the handler for the signal. So you have a single API sequence that actually calls sygaction, but then whenever the kernel would transfer execution to the signal handler, you can actually launch another API sequence. And a similar thing happens with clone, because you can be executing one set of syscalls when before the clone, then do the clone, and you can be executing one set of syscalls in the program that was cloned in the parent, but then you can be executing a different set of syscalls in the child. And it's kind of similar to what most syscalls do, but it's still a little bit different, because if you're fuzzing these syscalls, you have to be accounting for that. So you have to remember that you can actually divert the execution in this case, and you need some way to describe those kind of inputs. And there are also two or maybe more examples that are also kind of like different. And the two examples that I have here is BPF and KVM. And the difference with those is that instead of just accepting structures, like static structures, they actually accept code that consists of instructions. And the problem is that whenever you generate that code as a sequence of valid instructions, even those instructions are valid, the code might still not be like valid in general. So for example, if you try generating just random sequences of BPF instructions, the BPF verifier is going to reject them in most of the cases. Same thing can happen with KVM. You're generating random instructions. Even though the instructions are correct, one of your instructions can cause a null pointer dereference, or like dereference some random address, and that's going to crash almost immediately. So just by describing correctly those instructions separately, there's no way to go very deep when you're fuzzing this kind of inputs. right? So this is something that I call script-aware fuzzing. And I think this is something that needs to be approached differently. I saw an approach that's called Fuzzily, and this is a fuzzer that is used to target JavaScript calls. I mean, JavaScript parsers, JavaScript, what do they call it, like virtual machines, because they have the similar issue. You can't just generate random JavaScript code. It needs to be correct in some way to actually trigger anything interesting. All right.
Andre, we have one question
Yeah.
in the chat. Does fuzzing examine the correctness of outputs or just examine whether the kernel will crash?
Yeah, it's so by the correctness of outputs, you mean you pass, as far as I understand, the question is about, so let's say we can be passing random inputs into the kernel and waiting until it crashes. But then we can be passing random inputs into the kernel and checking whether its behavior is correct. So fuzzing can be used for both. I don't know of any examples of people. Actually, I think syzkaller, what Dmitry tried to do with syzkaller is, so there is something that's called gvisor, and gvisor is an interpreter of Linux programs in a way. So what you could do, and it's supposed to work exactly as the Linux kernel, but instead it's written in Go and runs in user space. So what you could do, you could try to run a sequence of syscalls against the kernel, and then try the same sequence of syscalls against the gvisor and compare the results. And if gvisor, so gvisor claims to be identical to the kernel, I mean, within some limited sense. And what you could do is you could actually check that the behavior, or like the output of the kernel and the output of gvisor is the same. So this is something that you can do. And this is something that's been applied quite a few times to different, in fuzzing, when you have two implementation of the same algorithm, what you can do, you can just provide different, like the same inputs to both algorithms and compare the outputs. So this is something that the fuzzing can be used for. All right. All right, let's look at the external inputs from the point of view of input structure. So if you look at network packets, they might seem like random data, but actually it's more like API. An example of that, actually, let's look at TCP, like TCP connection process. Let's say our kernel or our machine, Linux machine, has a socket, a TCP socket in the listening state. And externally, we're trying to connect to that socket. So the way this works, you send a sync packet, you receive an ACK packet, and you send the SYNACK packet. The problem here is that when you receive the ACK packet, it's going to contain a sequence number. And to actually establish the connection, you need to parse out that sequence number and use it in the SYNACK packet. So this is like an API. You kind of like parsing a response, you're getting a return value, and you're reusing this value in a subsequent call. The same thing happens with HTTP cookies. Although network packets might be a little more difficult because you can be expecting, so you're not only getting responses to your calls, you can be getting responses at any point of time. So this is something that's similar, but actually more complicated. And then USB is also quite weird. So USB is actually fully host driven. So if you're trying to emulate a USB device, you're not making API calls or calls of any kind. You are responding to them. And you don't actually know which kind of call is going to arrive next. So your fuzzer has to account for that. And this is something that's very unusual about kernel inputs. So the overall idea here is whenever you're trying to write a fuzzer, you need to understand what kind of inputs do you have. And you need to generate and mutate those inputs accordingly. Right, no questions. All right, let's keep going. So now let's talk about code coverage. So to do code coverage guided fuzzing, we need some way to collect code coverage. And there are three approaches that people usually use. The first one is using compiler instrumentation, and that's what KCOV is for. I'm gonna have, if we have the time, a whole big section about KCOV at the end. But the idea is that you're relying on a compiler to insert certain types of callback into your code, and then from those callbacks you collect the trace of execution, and that's how it works. Then you can use the emulator. So let's say you're running a kernel in the emulator, and emulator, what it does, it has a loop that executes instructions one by one. So what you can do, you can just hack into this loop and dump out extraction pointers. And this way you can get an execution trace. And people have been doing it for QEMU, they've been doing it for Unicorn, there are probably other implementations for other kinds of emulators. And finally, there is an approach of using hardware tracing features like Intel pointer trace. There's something similar for AMD as well. And the way it works, basically, there is a way to tell your CPU, like I want to trace this particular, like I want to trace the CPU, and the CPU is going to start dumping out trace into some particular address in physical memory, and then you can inspect that afterwards and rely on that for code coverage. Okay, so I answered the 2 questions about inputs. Let's move on to the 3 other questions. And these ones, I'm going to just briefly cover them. So first, how do we run the kernel? There are 2 typical approaches that you can use. The first one is using physical device. The second one is using a virtual machine or an emulator or something like that. The good thing about using physical devices is that you execute the kernel in its native environment, which means you will have all the proper hardware, and you can actually fuzz device drivers. When you're fuzzing in the emulator, you're kind of only limited to what the emulator can emulate. But generally, if you're fuzzing a very generic core subsystem of the Linux kernel, it doesn't really matter which approach you use, because both should work just fine. Then the bad thing about physical devices is they're hard to manage. So they're hard to restart, they're hard to get kernel logs from, they're hard to debug, and other stuff like that. And also, if you're running your fuzzer as root on your device, there is a chance it can get bricked. So in case of the emulators, this is very easy to deal with, because if for example, your kernel hangs, you can just kill the virtual machine, you can just restart it anytime. Most of the emulators have some GDB stuff, so you connect a debugger, and most of them provide a way to collect kernel logs. When it comes to scalability, I'd say, it's much easier to spawn more VMs than to buy more devices in case of using physical devices. But that's, the only problem with buying more devices, you might encounter that in case you're trying to fuzz some device that's really hard to acquire. So you will, let's say you just have a single device and you can't actually get any more. So that's something that can cause a problem in case you are trying to scale it up. All right, now about how do we...
Andre, one question. I think the question is answered, but I just want to give you a chance to see if you have more to add to this. If the fuzzer runs on the same host as the kernel that is fuzzed, then disrupting the kernel may prevent test results from being collected. Do we generally run the test from a second host?
Yeah, it's a great question. This is actually true. So I'd say this can happen, although in practice, when you're running a fuzzer on the same device that is being fuzzed, typically you still have enough time to somehow pass, or it depends on how the kernel crashes. If it's a really hard crash that kills everything, of course, you will not be able to even realize that something happened except that device crashed. In case of the kernel, usually the crashes are soft. It means that the kernel still can be working in a certain way, so you can still have some communication channel to the outside world. But this is certainly a thing that can be hard to deal with. But in case you're running it in an emulator, so you can actually, it depends on your emulator, but some emulators allow you to actually save the full trace of what's been happening inside, and this is something that you can rely on. So even if the kernel dies and it has your fuzzer that runs inside the emulator as a user space application, it dies together with the kernel, you can still use the crash dump from the emulator to observe what's been happening. So I'd say there's no good answer to this, but this is something that definitely can happen, and you should be able, you should be thinking about that when you're making a kernel fuzzer.
Thank you.
All right. let's move on to detecting bugs. So how do we detect kernel bugs? Dmitry Vyukov gave a session about this last week. This was also a mentorship session. So I definitely recommend watching that and checking out the slides. And the TLDR is just use the dynamic bug detectors that we have for the kernel. We have a lot of them. Most notably, we have Kazan for detecting memory corruptions, but we also have for detectors for info leaks, for data races and stuff like that. The only thing that I would add to this list is you can actually write.
一定会懂，100%会懂。这个越快。
I think someone accidentally unmuted.
Yes, I think that is the case.
Okay.
If you have a question, please ask. Yeah.
Yeah, anyway, so the thing that I would add to this list is you can actually write your own bug detectors. You don't have to write something really as complicated as Kazan. You can just add some asserts into the code that you're trying to fuzz. For example, you know that in some particular place, a particular subsystem is vulnerable to a particular like logical fault or something like that. So instead of trying to generate a test case that crashes the kernel, like after that logical fault has happened, you can actually add an assert and try to find a test case that triggers that assert. This is something that can be useful in certain places. And when it comes to automation, of course, there is a lot of stuff you can do. You should, ideally, if you're writing a fuzzer by your own, what should you targeting for is, for example, you should be able to just leave the fuzzer running for the night. You go to sleep, then you wake up in the morning, you check out the fuzzing results. And you should be automating up to that point at least. So you should write some code to monitor kernel code for crashes. You should restart crashing VMs of physical devices in case you're using physical devices. Some more advanced stuff like deduplicating crashes. This is the case where we have multiple crashes. They're a little bit different, but still this is the same root cause. So you can actually like bucket them, put them into the same bucket so you don't have to inspect all of them. Then you can generate reproducers, and even at some point you may reach the point where you want to report bugs and track fixes automatically. Actually, if you reach that point, you probably should just reuse syzkaller or base your fuzzer on top of syzkaller, because syzkaller already is doing that, so you don't have to do it on your own all over again. Right, any questions about that part?
Don't see any questions at the moment.
Okay, so let's briefly look at the two fuzzers. The first one is called Trinity, the second one is called syzkaller. And these are the two fuzzers that like the two stepping stones in terms of Linux kernel fuzzing development. So Trinity appeared many years ago, and this fuzzer essentially is doing what? It's running an infinite loop, and it's trying to call different syscalls in this loop. So this is a fuzzer that does not generate inputs in the sense that I mentioned before. It doesn't try to generate a sequence of calls as an input. It's just trying to generate an infinite sequence of syscalls. But this fuzzer is still API aware in some sense, because it knows about different kinds of syscalls, and it knows that some syscalls are supposed to be accepting these particular structures, and it tries to generate those structures. But there is no coverage guidance or any guidance in any other sense. So syzkaller was a huge improvement. It was started, I don't know, like 5 years ago, and syzkaller is something like Trinity, but better. So first of all, syzkaller introduces a notion of a test case. So instead of just generating an infinite stream of syscalls, it generates a finite sequences and executes them. And also includes isolation for running those sequences. This isolation is not perfect because syzkaller still reuses the same kernel to run multiple inputs, but it's as good as you can get. So it tries to use different kind of sandboxes, namespaces, and stuff like that. Then it is coverage guided. I mean, the moment you have a notion of a test case, that means you can actually mutate those test cases, and you can use the coverage guided approach, and it relies on KCOV for that. And instead of hard coding all of those descriptions of different syscalls and structures into its implementation, it provides a language to describe them. This language is called syzlang. And finally, it introduces a lot of automation. So a Trinity is usually binary, and just run that binary, and everything else you have to do on your own. So you have to monitor the kernel output on your own. If your VM crashed, you have to restart it on your own. syzkaller has all that built in, And also it even goes much further, and it introduces something that's called syzbot. And syzbot is it's a few dozen of syzkaller instances that run in the cloud. They're targeting mostly the mainline kernel, but some of the other kernels as well. These syzkaller instances, they are automatically reporting all of the bugs that syzkaller finds. And essentially, syzkaller is something that goes deeper due to coverage guidance. It finds more bugs and it's easier to extend. But Trinity is still, even though it finds less bugs, I think it's still useful in certain cases because it's really easy to deploy as a binary. You just build it, you drop in the binary, you run it, and that's it. syzkaller can also be run in standalone mode, but it's a little bit more difficult to set up. All right, so what I'm going to talk about next. So, okay, this is what's all the theory about kernel fuzzing. Now, if you want to be doing kernel fuzzing, your question is like, what do I do now? Like, how do I approach this? What can I do? And I want to describe these 4 approaches briefly. And these are the approaches that I've seen people doing, and all of them have been successful in a certain way. So the first approach is to build kernel code as a user space application. The second one is to reuse a user space fuzzer. And third one using syzkaller, and the fourth one is just writing fuzzer from scratch. Actually, see a question in the Q&A box.
Yes, go ahead. Fill the question.
Yeah, okay. The question is, I've seen KVM-specific syslang descriptions, but I was wondering if QEMU is used to launch kernel, then does nested support, and then does nested support has to be enabled on host in order for further to use KVM-specific syscalls? Yes, as far as I know, the way KVM fuzzing works, so you do run fuzzer in QEMU, you do enable nested support, and inside of QEMU, syzkaller tries to create another, like a nested virtual machine. But instead of using something like QEMU KVM, it has an implementation of its own KVM machine that's designed specifically for fuzzing. I hope that answers the question. I'm gonna actually link, if you want to see more about how this works, I'm gonna, in one of the next slides, I will have a link to the implementation of this particular part so you can check it out. All right, let's get back to our approaches. So the first approach is building code in user space. And this works great for the code that's actually easy to separate from the rest of the kernel. I mean, the great thing about it that you don't need to bother about emulators, you don't need to bother about kernel, like virtual machines. You can just reuse all of those nice tools that we have for user space fuzzing. And here's a couple of approaches that people have been doing. The first one is for fuzzing BPF. So what they did is they actually moved the BPF subsystem kind of like out of the kernel, so they would run the verifier in user space, and I think some other parts of BPF as well. And the second approach where they've been fuzzing the ASN1, this is like a fuzzer for crypto keys. They actually also moved it to user space and fuzzed it there. So this works in case your subsystem, like the parties you want to target, is easy to separate. But for most of the kernel inputs, that is not the case. Right, the second approach is to reuse a user space fuzzer. And in this case, you just take a user space fuzzer, you can take AFL or libfuzzer. This is other fuzzers that people usually use for fuzzing user space application. AFL was the first fuzzer to actually introduce coverage guided approach, but the problem with that was that it would actually read all of the inputs from a disk, which is quite slow. Then there was libfuzzer that, and also, as far as I remember, AFL, the first version used, instead of using compiler instrumentation, they would do some dynamic binary, or like they would rewrite the binary dynamically to extract the coverage, which was quite painful. And then libfuzzer came and introduced coverage guided fuzzing with compiler instrumentation, and instead of reading inputs from the disk, it would read them from memory. And there are also many other user space fuzzers that you can use. So instead of, if you take user space fuzzers, so first of all, instead of calling a function of a user space library, like the thing that you normally do when you're fuzzing user space apps, you interact with the kernel. For example, you call a particular syscall or a sequence of syscalls. And the other thing that you will need to do, you will need to plug kernel coverage into the fuzzer. So all of the user space fuzzers, they rely on a certain type of coverage that is of the kernel, this is completely different. And this works fine for fuzzing inputs that accept blobs of data like file system images, certain netlink stuff, and other stuff like that. But usually, as we discussed, kernel inputs aren't blobs. In case you're fuzzing syscalls, it's a sequence of syscalls. So you would want to somehow like be mutating sequences of syscalls. So you need to write some kind of generator or mutator for those inputs. And one of the approaches that I saw, it's actually about fuzzing the XNU kernel, which is an iOS kernel, but you can apply the same idea for Linux kernel. So what they did there is they would turn structured aware fuzzing into API aware, but by basically representing a sequence of API calls as an array of structures. And then you write a custom generator mutator, and that just works. All right.
Andre, if this is a good time, there is a question in the chat. Or stateless, or they imply the chain of dependent API calls. If they are stateless, is it possible?
Every input, right? So you have two approaches. You can you either approach this as a like a stateful approach in case you don't restart the kernel and you're going to be getting something like Trinity. But in this case, if you're using coverage guided fuzzing, it might break because some of the inputs that you previously used might leave some state in the kernel. Or what you can do is you can try to sandbox those inputs, like so they don't they don't produce any side effects between them. And this is something that syzkaller does. And it's really, this is not an easy thing to do. I actually recommend to check out some of the syzkaller talks to figure out how it's being done in case of syzkaller. But yeah, this is definitely a problem. Another thing that I saw people doing, I don't think I have any links here, but instead of rebooting the kernel after every input, what you can do is called snapshot fuzzing. So you save the snapshot of whatever state you have in the kernel before running your first input, then you run the input, then you reverse the snapshot. Of course, to do this efficiently, what you would need some kind of emulator that allows you to actually take snapshot quick and restore the previous state. Right, I hope I answered this question in some way. All right, let's move on to syzkaller. So there's been a lot of syzkaller talks over the last years. I don't want to go over like each of them in details. I don't want to mention the same stuff in details. And the thing that I want to say is syzkaller is really good to fuzz API-based interfaces because this is what syzkaller was initially designed for. And usually if you have something that looks like an API, like a syscall sequences with structured arguments, and there's just simple stuff like passing return values between them, you should use syzkaller. It's a great tool. Some tips about using syzkaller. The first one is don't just fuzz mainline with the default config, because I mean we already have sysbot that fuzzes the mainline kernel with the like a bunch of config options enabled. And if you're going to be fuzzing it locally, most likely you will not find anything new. So to actually find some new bugs, what you do with syzkaller, the first thing that you can do is to add new descriptions. The second thing you can do is to tighten attack surface, which means instead of trying to target all 300 of syscalls that the kernel has, just choose 3 of them. And it usually works great if those 3 are related. So in case of network fuzzing, for example, what I've been doing for a long time is I would enable like the TCP sockets, I would enable the send syscall, the receive syscall, and set socopt. And I would be fuzzing that, like 4 syscalls, just those 4 syscalls. And something else that you can do is to fuzz distribution kernels. This way you can actually detect bugs that have been fixed in the mainline but haven't been fixed in the distro kernels. Then something that I want to mention is that syzkaller is extensible. You don't have to just use syzkaller as is. And first, what you can do is you can build your fuzzer on top of syzkaller. And regarding to that KVM question that was before, so here are the links of the KVM fuzzer that's built on top of syzkaller. So there is actually a separate package called ifuzz within syzkaller to generate x86 instructions, valid x86 instructions. It still suffers from some of the issues that I mentioned, like you still have to generate valid sequences of instructions to go very deep, but it tries to address them in other ways. So just check out these files that I've provided. And what I also did is I also built a USB fuzzer based on top of syzkaller. If you recall, USB inputs are not API based, but what I did here is I actually managed to, well, basically with USB fuzzing, what I did is I introduced a notion of an API call, and that API call would receive a request from the host and try to understand what request this is. And based on the request, it would generate a response. So this is something that can be done, and you don't have to just run syzkaller as is, you can build on top of it. And finally, you don't even have to build on top of syzkaller, you can just reuse some parts of it. For example, the crash parsing code or the VM management code. So syzkaller actually has a code to manage different devices, different types of devices that syzkaller can run on, and it's all behind the same interface. So there is the same interface for managing QEMU instances, there is the same interface for managing Android phones and stuff like that.
Andre, we have a few questions if you want to take them. The first one is, have you considered generating fuzzing scripts as correct sequences of system calls using the model-based testing approach when we have some formal models for describing the behavior that is allowed?
No, I have not considered that. I've never heard about model-based approach, but so yes, I mean, generally, I can't say that I've considered any particular approaches to resolve this kind of questions, but I wanted to point out that generating instruction sequences is something that, okay, sorry, I was confused because it says generating fuzzing scripts as correct sequences. Okay, anyway, the answer to this question is no, I've never heard of model-based testing, but maybe this is a viable approach that you can use. Yeah, I was confused. I thought this question is about like instructions in terms of KVM, BPF, and stuff like that.
Okay, that sounds good. Thank you. And the second one is, so if fuzz produces, if fuzz, I'm not quite sure what the question is.
ifuzz. This is ifuzz is the it's the syzkaller part that generates x86 instructions. Yes, it produces guest code, correct?
Okay, great.
So there's actually, if you're talking about, how are we doing on time, by the way? Yeah, it's fine. Yeah. Okay. So in case of ifuzz, there is actually what's called a pseudo syscall. It's like an API call that tries to set up a guest, like a guest VM into some interesting state, a guest CPU into some interesting state. And then there is the ifuzz part that tries to execute random instructions inside this guest. This is how it works briefly.
Okay, one more question. Have you tried to use a symbolic execution to assist fuzzer? Have you tried symqemu, QEMU to fuzz kernel?
Yeah, I've never tried that personally. I saw people doing that. I'm going to have some links at the end of the presentation where you can check out some papers that people are trying to do that. So I haven't tried that, but my overall impression is that symbolic execution works in certain limited cases, but it hardly works for such hard targets as the kernel. Because I mean, symbolic execution is you're trying to generate the next input based on, so you kind of trying to figure out what kind of input should you use to actually go deeper into the code. And you're like trying to solve a set of equations. In case your target is really big, there is a lot of equations that you need to solve, and it kind of is getting slow.
One more question, Andre. Does syzkaller specifically try to generate test cases which trigger code paths who are not covered yet?
No, not as far as I know.
So the
So
second
this
part
is
of
something
the,
that's related to symbolic execution as well, but yeah, it's not trying to do that, no.
okay. Second part of that question is, does it explicitly try to trigger the code lines which their color is red in syzbot, or does it just try to cover new coverage?
Yeah, it just tries to mutate the inputs that you have, and if they cover something new, that's when it registers them, but it does not specifically try to apply mutations to try to cover new lines of code. No.
Okay, thank you. That's all we have right now.
Okay. Right, the final thing that is the final approach that I wanted to mention is writing a fuzzer from scratch. And this might work really well for targeting some weird, like for writing a targeted fuzzer for some interface that is not API based. And instead of going on into a lot of details about that, I've linked here 3 articles, and I definitely recommend reading all of them. So the first one is about writing the world's worst Android fuzzer. And what they're doing there is just trying to go through different kinds of device files that an Android phone has and try to write and read data from them. And that actually works for crashing Android phones. The second one is also really interesting. It's about eBPF fuzzing, and they're using kind of like a hybrid approach there because they manage to, they run the BPF verifier in user space, and they're fuzzing it in user space and trying to generate a sequence of BPF instructions that passes the verifier. And then they pass the same sequence of instructions into the kernel and try to figure out if these sequence of instructions can trigger a bug in the kernel. And they're also using a very interesting approach to actually detect logical bugs within BPF programs in the kernel. So definitely worth checking out. And the final article is about fuzzing the x86 entry code. This is yet another type of inputs that the kernel has. Instead of just trying to target the syscalls, what they're doing is they're trying to set up all the registers in like weird states and then trying to call different kinds of instructions that are supposed to call a system call, so like that. int80 or syscall instructions or other stuff like that. So definitely recommend checking all of these articles out. Right, any questions?
No, not at this time.
Okay, now I want to share some generic fuzzing tips. And the first one is read the code. So the idea here is the ultimate target that you're trying to fuzz is the code. So instead of relying on some documentation or some specs, like in case of USB, I read a lot of USB specs, but then I ended up writing those are not always relevant. And what you should do, you should try to read the code. You should understand what kind of inputs it expects, how it behaves, and based write a fuzzer based on that. And also, what really helps is that when you're fuzzing some particular subsystem, you should identify a part of code that you're trying to target. And if you're doing coverage guided fuzzing, the part of code that you're trying to cover. This really helps. The second thing that I wanted to mention, let's say you wrote a fuzzer. So how do you know if this fuzzer is any good? These are some simple tips. The first one is check code coverage. So you don't only use code coverage for guidance, you can also use it for inspecting what your fuzzer does. And if you followed my previous tip and you actually identified the layer of code that you're trying to target, the part of code that you're trying to target, just make sure that your fuzzer covers it. Then what you can do is you can actually inject bugs into the code that you're trying to fuzz and check the fuzzer finds them. Or you can revert fixes for certain bugs or CVEs and also make sure that your fuzzer finds them. So this is in case your fuzzer does not find any real bugs, just make sure that it can find at least injected bugs or the bugs that were in this code previously. And another thing that I wanted to mention, there is something that's called if you have a fuzzer, you can work on 2 things. First, you can work on improving how fast it is, which means you can try to achieve more execution per second. Or you can improve how smart it is. So you can improve the way you generate inputs, you can improve, maybe use some more relevant guidance, signal, or maybe some other stuff. And my general tip is to focus on smart first before focusing on fast. It would be really interesting to see if this, I mean, this is my experience, and it would be interesting to see if there is like some formal, if there is a way to formally verify this. I actually saw this paper. I don't, sorry, I've linked this paper. I mean, when I share the slides, you can check out the paper. It's about something similar, but still a little bit different. So it would be interesting to see whether focusing on smartness is actually a better approach than focusing on making fuzzers fast. All right. Any
Quick
questions?
question, Andre.
Mm-hmm.
What is the first question is simpler one is, what is the paper and called or authors?
Okay, let me open it. I'm gonna copy the name into the chat. I mean, I'll share the slides later, so.
That's good. So there is a there is a question that's rather long. Do you want me to read that out, or will you be able to check the chat? I can read it out.
Okay, I see. Okay, for fuzzing complex ioctl handlers, they have really. Yeah, sorry, let me read it first. Okay, this is the question. As far as I understand, it's about whether we can actually use this symbolic execution to guide our fuzzing, and can we build that into syzkaller? The answer is yes, we can. The question is if you can actually manage to get it working and working fast enough. Because if you're trying to generate your input and you're trying to solve equations for 1 hour, then obviously it's not worth it. I mean, unless the result of your solution to this equation is the input that actually triggers a bug immediately. So this is something that you can do, but nobody actually implemented that. So that, I mean, yeah, there's no implementations that I know of that work good.
Okay, so there is one more question in the question Q&A. So does syzkaller provide valid eBPF programs when fuzzing?
No, syzkaller generates valid eBPF instructions, but then the eBPF program that syzkaller generates is just an array of those instructions. So it might work okay in certain cases because the instructions that are generated, they're good. I mean, there are arithmetic instructions, there are instructions that tries to access BPF maps, but syzkaller does not try to generate a consistent input in terms of a single program, like a sequence of instructions. It just tries to generate those instructions separately. And I think this is something that can be improved within syzkaller, and you can achieve some interesting results with that.
Thank you.
Okay. All right, let's talk about the final part, which is about collecting coverage with KCOV. And so what's KCOV? KCOV is a tool that's specifically designed for fuzzing and for collecting code coverage from the Linux kernel. It's available upstream. You need to rebuild the kernel. You need to enable config KCOV. And the reason you need to rebuild the kernel is because KCOV is based on compiler instrumentation. And it's able to collect coverage from both user threads and background threads, and also software interrupts. And the second part requires kernel code annotations, but I'll describe that in a second. So first, how does it work? The way it works is it enables a certain GCC and Clang flags to insert callbacks into each basic block. So consider if you have an if clause, it's going to insert a callback before the if clause, inside the if clause, and after the if clause. And then all of those callbacks are used to actually collect a coverage trace. So the way you use it is there is a debugfs interface. You open syskernel debug kickoff. You mmap the buffer. This is the buffer where the coverage will be collected. And you call the kickoff enable ioctl. Now, after you do that, whichever syscalls you execute, coverage that happens in their handlers will be collected into this mmap buffer. So this is done like each sanitizer cov trace PC call will see that kickoff is enabled, and it will know that it's supposed to put coverage into this mmap buffer. So KCOV collects coverage from the current user thread by default, and this is done on purpose. The reason is that, let's say you're trying to execute an input, a sequence of syscalls, and to do coverage guided fuzzing properly, you would only want to collect coverage that is relevant to this input. And since the kernel has a lot of different stuff happening in background, there are interrupts, there are different kinds of threads scheduled and executing, you don't want to collect coverage from every single thing that's happening in the kernel. So initially, KCOV has been designed so it only collects coverage from syscall handlers that happen synchronously. There's a problem, though, with this approach. I mean, it works, let me put it like that. It works great for what syzkaller has been doing, and I mean, yeah, anyway, it works great. But there is still a problem with this approach. And the problem is that if you have an input that you're trying to execute, some of coverage that's still relevant to this input might be executed in some background code. So an example would be, let's say you have a device handler, and when you open this device handler, or like when you create an instance of this device, you open a device file. A background thread is getting created, and then the data that you're writing into the device is actually handled by the background thread instead of being handled synchronously in the syscall. So in this case, you will not be seeing this coverage when fuzzing. So we've tried to address this with a KCOV change. And the solution that we came up with is that we thought about, like, can we actually somehow automatically decide which coverage is relevant and which is not? And in certain cases, it's not possible. So instead, we went with the approach of actually annotating the parts of the code in the kernel to collect this background coverage. And the way this works is, let's say you have some background thread, and there is a section of this in the thread implementation that you want to collect coverage from. So what you would do, you would put two calls. The first one is called KCOV remote start. The second one is called KCOV remote stop. And since you need to somehow understand like which thread you're collecting coverage from, there is a unique ID that's assigned to each of those sections. Now, this was the initial idea. Now, the problem is that you have a lot of different background threads, and they might be using different IDs, but how do you pass this unique ID from user space? Or maybe how do you know to which thread a particular unique ID belongs? So let's say you have a particular background thread, and you only want to collect coverage from that. How do you actually connect to the thread and do that? So for this part, syzkaller actually makes, or KCOV actually makes distinction between two different types of kernel threads. I call them global and local. I don't think that's the official kernel name. I don't know if the kernel even has an official name for that, but that's what I call them. So global background threads are the threads that are spawned from init code during boot typically. And typically there is a fixed number. For example, you are booting the kernel and you have a single network device. And the network driver for this device will spawn two threads, one for handling the input data on this device, one for handling the output data for this device. But then you have something that I call local background threads. And these are the threads that spawn from syscall handlers. And let's say you're opening some device file, and inside the syscall handler for this device file, a new thread that handles this particular instance of this device file is created. And KCOV makes a distinction between those. So for global threads, there is no easy way to pass these IDs from threads to user space or from user space to threads. So what we do is we use predefined IDs. Let's look at an example. This is a hub event thread, and this is a global thread that is spawned for each USB bus when the kernel boots. So this thread handles all the USB data that is going through a particular USB bus. And the way we do, so we have the KCOV remote start and the KCOV remote stop annotations in there, but what kind of ID do we pass? So we pass an ID that's fixed. I mean, here actually use KCOV remote handle, and so KCOV remote handle, just think of it as a simple function that actually mixes its two arguments. So something that we wanted to address here is to make this extensible. So the ID is generated based on subsystem ID, and in case of USB, based on the bus number. And the way you would collect coverage from this particular global thread is you would issue a KCOV remote enable ioctl instead of just KCOV enable, and you pass this particular ID into the handles array of that of the argument of that ioctl. So you can connect to multiple threads, and you need to actually know which IDs the threads use. And the definition for this KCOV remote handle at KCOV subsystem USB is actually put into a UAPI header, so it's available to both the kernel and the user space. So I don't know, was this clear? Are there any questions about this part so far? Right, let's keep going then. So this is for global threads, but then for local threads, it's actually simpler because local threads can be created from, so they are created from syscall handlers. That means we can actually pass unique IDs from user space. And the way this works, you also use the KCOV remote enable syscall, and you use a different argument of the structure that's passed. Or you use a different field of the structure that's passed to this ioctl, and the field is called command handle. So what this ioctl does, it actually saves this command handle inside the current pointers. Current points to the current user task. There is when KCOV is enabled, there is another field inside the current task struct, and it's called KCOV handle, where the command handle is getting saved. And then in the syscall handler that actually creates that local thread, what you do is you take that KCOV handle from the current and you pass it into a structure that passed to this thread. So normally whenever a kernel thread is created, some kind of data is going to be passed through it. And in this case, we're looking at example of vhost. And whenever you open a def vhost device, this function is going to be called, and it's going to create a thread that handles this device. So what we do here, we take the KCOV handle and we pass it through def. And then inside the implementation of the thread, what we do, we take the handle that we passed and we call the KCOV remote start and KCOV remote stop. So this way, we can actually pass a common handle from a single KCOV remote enable call and to collect coverage from all the local threads that have been previously annotated. Right. Something that you need to keep in mind when you're using this stuff is when you're fuzzing from multiple processes in a single VM, there is an issue with global threads. So the issue is that if you want to be fuzzing from multiple processes, you want to know which global, if there's only a single global thread that handles inputs from all those processes, there is no way to know which coverage is related to each input. So what you need for using KCOV with global threads is you actually need a separate global thread for each fuzzing process. And the only actual user right now in the kernel of this feature is USB. And with USB, we create a new USB bus, a dedicated USB bus for each fuzzing process. And this way, each fuzzing process has its own, each USB bus has its own background thread, and each of those background threads has its own ID. So the fuzzing process can connect to that background thread and only correct coverage from it. For local threads, though, you don't have any problem. You can create multiple threads within the single syscall handlers, or within the single program, you can call multiple syscalls that create threads, so it's all going to work.
We have a question, Andre.
Yeah.
Is there a user space utility to parse the output of syskernel debug KCOV? I mean, similar to strace on some program.
There are some tools. So if you go to syzkaller repository and you check out the tools directory, I think there's something that's called I don't remember what it's called, but there is a tool to actually visualize the KCOV dump. So you pass the whatever you collected from KCOV, you pass the kernel image, and it's going to actually show you it's the same thing that you see on syzkaller dashboard. So it's just going to show you which lines are covered and which lines are not. So just check the syzkaller tools directory.
There is another question, which is also long in the chat. Would you like to take a read that? I think it might be hard to follow if I started reading.
Okay, this one is still about symbolic execution. Say in an ioctl handler, we have a case statement like cmd equals that beef. Would it be worth extracting statements like this in advance before fuzzing with syzkaller, so we don't waste iterations trying to derive that beef before getting inside the case statement. Or will syzkaller with KCOV be able to figure out this easily? Yeah, it's a good question. So there is a single instance, like, okay, not a single, but there is a very important instance of this behavior that I saw when I was fuzzing USB. And when you're fuzzing USB, when you connect a new USB device, it passes a certain ID, like a device ID, vendor ID, to the kernel. And based on that ID, the kernel is trying to figure out which driver to load. And the code that tries to figure out which driver to load, it's basically a loop consisting of 3 lines. It goes through a list of device drivers. So whenever a new USB device driver registers itself in the kernel, it puts a link to itself into this list. So there is a very short loop that tries to go through all the kinds of device drivers that there are and tries to find out the IDs. So each driver has a set of IDs that for the devices that it handles, and the loop is trying to match the IDs of the device that you have with the IDs that are inside of the drivers, right? And the problem here is that if you rely only on code coverage, there is no way you're going to be able to connect or like to go into different kinds of devices, because the code is always covered. There's always at least a single instance of this loop that's being executed. And what we did here is we actually used exactly the approach that you mentioned. So when syzkaller tries to generate USB IDs of USB devices, beforehand we run a program that extracts all of the IDs for all of the drivers that are enabled in the kernel. And then whenever we generate a program, we actually use one of those IDs. So this is something that you can use in certain cases. This is one of the only ways to deal with stuff.
There is another question in the Q&A box.
Mm-hmm.
Since the last talk last week, I have been trying to fuzz a rooted Android device, but syzkaller attempts to ADB push syzfuzz during the boot, splash screen, and get a permission denied error. Do you know of any resources for setting up a syzkaller Android environment? And if not, anyone with experience using syzkaller for Android fuzzing? I have seen the setup docs on the GitHub. Looks like they're looking for resources for more help.
Yeah, I mean, you can check out the syzkaller documentation. Has 2 pages. The first one is called syzkaller talks. The second one is called syzkaller research articles, and they're both linked from the syzkaller main page. They might have some details, but I don't have an answer to this question. So what you have to do here, if you see that the fuzzer, you're using syzkaller, and you see that something is going wrong. For example, in this case, your syzkaller starts copying the fuzzing binary before the Android phone boots. That means there's something wrong, and the only way to fix that probably is just to go read syzkaller source code and try to fix it in there. So if no one, maybe your phone, your the Android version that you're using works a little bit differently than the one that's been used when this code was developed. So probably there is not going to be a straight up answer to this question. So the only thing to deal with this is to actually read the code, understand what's wrong, and try to fix it yourself. Right. Okay,
No
let's switch to the final part. A few final notes. The first one is developing fuzzers is engineering. So what I mean by this is that if you're writing a fuzzer, if you want to write a good fuzzer, you got to be good at writing code. So the reason that syzkaller has been such a success is because it has a lot of engineering experience and a lot of engineering thought put into it. And yeah, the better, like you can't, okay, anyway, that's what's the point. So anyway, you gotta be able to write code. And the second note that I wanted to give is, I think we've reached the point where whenever you have a good fuzzer, it finds a lot of bugs. So if you look at syzkaller dashboard, there's going to be a few thousands of bugs, and not all of them are dangerous. So fuzzing became kind of like the new static analysis, in the sense that static analysis produces a lot of bugs, but most of them are false positives, right? And unfortunately, none of the bugs get fixed. So there's no way for let's say you're trying, as a security researcher, you're trying to find bugs that matter. If you have a few thousand bugs, it's going to be a very hard work to actually go through each of them and try to figure out what each of them does. Something that might be one of the interesting approaches that I would like to see in the future is trying to figure out which bugs actually matter. So if you have 1,000 bugs, maybe there is some approach to find out which of them are exploitable. So this is not something that I've seen. I've seen some papers that are talking about automatically exploiting bugs, and this is a step in the direction that I would want to see people going. Just a side note. And then I have a list here of different kinds of materials you can check out. First of all, there is the first two links is just a collection of links to articles, and I mean the first block of links is a collection to links, article, research papers about kernel fuzzing in particular. So there is a lot of them you can check out. You can check them out. Then a few people to follow on Twitter. First of all, you should follow Dmitry Vyukov, who is the author of syzkaller. Then there is Gamoza Labs, who is Brandon Falk. And I'd say if you're interested in doing more advanced fuzzing stuff, this is the person that you would want to follow. He's actually doing streams on Twitch where he takes some target and tries to fuzz it. And a few months ago, he's been fuzzing an Android phone, which was a really interesting thing to watch. So definitely you can check out what he does. And then whoever else's work or whoever else's article I mentioned in the talk, you can also find out what they do, follow them. And then finally, there is a Telegram channel where I post the links that are related to Linux kernel sometimes. So you can also find some materials there. All right, do we have any more questions?
A couple of questions we have. How does syzkaller deal with kernel code that triggers timers?
Kernel code that trigger timers. I mean, can you give an example? I'm not sure what exactly this means. So maybe you mean like, how does it deal when you have maybe you have a syscall handler that actually, instead of doing stuff on its own, it creates a timer and does it in a timer. So in this case, if you want to be doing, so syzkaller doesn't really have any specific handlers for these cases. I'd say the thing that you can do if you want to be collecting relevant coverage is to actually use the remote KCOV coverage stuff that I mentioned. So whenever you have a timer, it's typically executed in a software interrupt context. And whatever I mentioned about background threads, you can use the same annotations to annotate interrupts. And this way you can actually connect certain types of interrupts to certain types of inputs with syzkaller. But this is something that you have to do manually.
So there is a follow-up. Does it collect a coverage for the code that runs in the timer? I think that's...
Yeah, that's what I meant. So by default, no, because it's soft interrupt context. And KCOV ignores that, but you can use the annotations. And the only thing, there are some limitations. So if you actually open the, well, anyway, you should try it. There are some limitations to when it works, but this is fixable. There are, like, I've only implemented it as far as the cases that I saw. And in some certain cases, you may need to also work on KCOV a little bit. So you have to improve KCOV, but generally it should work, yeah.
One more question. Systems may be particularly vulnerable to boot. Is there a way from, for example, boot args to start fuzzing early, maybe from a special systemd unit?
I've never thought about that. Yeah, I mean, maybe there is. Sorry, this question is something that I don't really know what to answer.
Okay. That's an interesting question, because sometimes early bugs, you know, or sometimes we do not know how to debug. Yes, that's a great question. But okay, that's any other questions?
That makes me think. Yeah, sorry, that's not something related, but that just made me think that maybe it makes sense to try to make a fuzzer that tries to fuzz boot arguments of the kernel. Maybe someone already did that. I mean, this is something completely different, and it's more about finding stability bugs than security bugs, but still, that would be interesting.
Great. Any other questions? we're coming up on almost, we have 5 minutes left at this point. Okay, if there are no questions, thank you for joining us today. Andre, thank you for the talk. It's very informative and awesome. I want to leave you with some resources to continue your self-study and education. And we have a, and we really hope that this talk, this webinar today, and other webinars in the series will be helpful for you to continue your journey of learning and to be more effective and productive participation in the open source projects. We will leave you with a few additional resources for your continued learning. The Linux Foundation Mentorship Program is designed to help new developers with the necessary skills and resources to experiment, learn, and contribute effectively to open source communities. Outreachy Remote Internship Program supports diversity in open source and free software. In addition, Linux Foundation Training offers a wide range of free courses, webinars, tutorials, and publications to help you explore the open source technology landscape. Linux Foundation Events also provides educational content across a range of skill levels and topics, as well as the chance to meet others in the community to collaborate, exchange ideas, expand job opportunities, and more. You can find all events at events.linuxfoundation.org. Please continue your journey of learning, and thank you. Kristen, do you have anything to close with?
No, that's it. Thank you so much, Andre and Shua, and hope everyone has a great day. Thank you.
Thank you for inviting me.
Thank you, Andre.
Thank you, Andre.
Bye-bye.
Bye.